Today we'll discuss section 6.3, Euler's theorem. Before we discuss Euler's theorem, let me go back to section 6.1. Please take a look at Fermat's little theorem. Fermat's little theorem says that a to the power p minus 1 is congruent to 1 modulo p. Now, what is p here? P is a prime number. Question: what if p is not prime? Well, if p is not prime, we need Euler's theorem. Euler's theorem says the following: if n and a are positive integers that are relatively prime, then a to phi of n is congruent to 1 modulo n. Question is, what is phi of n? Please take a look at this definition. Let n be a positive integer. The Euler phi function phi of n is defined to be the number of positive integers not exceeding n that are relatively prime to n. Let us discuss examples. We start with 1. Since the only positive integer not exceeding 1 that is relatively prime to 1 is 1, we have the following: phi of 1 is equal to 1. Example 2. Let n be 2. Since the only positive integer not exceeding 2 that is relatively prime to 2 is 1, we have phi of 2 is equal to 1 again. Let n is equal to 3. Since the only positive integers not exceeding 3 that are relatively prime to 3 are 1 and 2, we have phi of 3 is equal to 2. So here we have two numbers. Phi of 3 is equal to 2. Let n is equal to 4. Since the only positive integers not exceeding 4 that are relatively prime to 4 are 1 and 3, phi of 4 is equal to 2, because here we have two numbers. Let n is equal to 5. Since the only positive integers not exceeding 5 that are relatively prime to 5 are 1, 2, 3, and 4, we have phi of 5 is 4. So here we have 4 numbers, therefore phi of 5 is 4. Remark: it immediately follows from the definition that phi of n is equal to n minus 1 if n is a prime number. Because if n is a prime number, there are n minus 1 numbers between 1 and n that are relatively prime to n. Now, question is it possible to find phi of n without counting numbers that are relatively prime to n? The answer is yes. Please take a look at Theorem 1. Let us consider the prime power factorization of n. Then phi of n is equal to n times 1 minus 1 over p1 without alpha 1 times 1 minus 1 over P2 without alpha 2 times and so on times 1 minus 1 over pk, again without alpha k. So we use these prime numbers without alpha 1, alpha 2, and so on, alpha k in the denominators. Let us discuss examples. We already know that if n is equal to 4, phi of 4 is 2, because the only positive integers not exceeding 4 that are relatively prime to 4 are 1 and 3. But now let us use this formula in order to find phi of 4. Observe that 4 is equal to 2 squared. Therefore, phi of 4 is equal to, here we start with n is equal to 4 times, and now over here we have only one term. P is equal to 2. So 1 minus 1/2 is 1/2. 4 times 1/2 is 2. Next, we already know that if n is equal to 5, phi of 5 is 4. Now let us get same result using the formula. So phi of 5 is 5, n is 5, times 1 minus 1 over 5. There is nothing else because n is a prime number. And now 1 minus 1 over 5 is 4 over 5 times 5, 4. Here's another example. N is equal to 2 cubed times 3 squared times 7. So this is n. We multiply n by the following: 1 minus 1 over p1. P1 is 2 times 1 minus 1 over p2. P2 is 3 times 1 minus 1 over 7. P3 is 7. We do arithmetic. The answer is 144. By the way, going back to this, one can get the same result using this formula. Note that if n is prime, n is equal to p1 to the first power. So n is equal to p1. We multiply p1 by 1 minus 1 over p1. There is nothing else here. So p1 times 1 minus 1 over p1 is p1 minus 1. And since p1 is equal to n, it is equal to n minus 1. Done. Next. Please take a look at this. A reduced residue system modular n is the set of phi of n integers such that each element of the set is relatively prime to n, and no different elements of the set are congruent modular n. Let us discuss examples. Let n be 8. These two sets are reduced residue systems modular 8. Here is why. First of all, observe that phi of 8 is equal to 4. Here's why. Let us go back to this formula. N is equal to 8. 8 is 2 cubed. Therefore, phi of 8 is equal to 8 times 1 minus 1/2. 1 minus 1/2 is 1/2. 1/2 times 8 is 4. So phi of 8 is equal to 4. Over here we have 4 elements, and over here we have 4 elements. Remember, a reduced residue system modular n is a set of phi of n integers. Here, indeed, we have phi of 8 integers. Here we have phi of 8 integers. But now, let us check this condition. Each element of the set is a relatively prime to n. 1 is a relatively prime to 8. 3 is a relatively prime to 8. 5 is a relatively prime to 8. 7 is a relatively prime to 8. Same is over here. Each of these numbers is a relatively prime to 8. Lastly, no two different elements of the set are congruent modular n. One can check that if we pick any two different elements from here, or any two different elements from here, these two elements are not congruent modular 8. To the contrast, these are not reduced residue systems modular 8, because over here we do not have phi of n integers. Over here we do not have phi of n integers. Over here we do have phi of 8 integers. However, 6 and 8 are not relatively prime. Next, let us go back to section 4.1. Please take a look at this. Do not confuse a reduced system of residues modular n and a complete residue system modular n. Complete system of residues modular n is a set of integers such that every integer is congruent modular m to exactly one integer of the set. By the way, take a look at this lemma. A set of m incongruent integers modular m forms a complete set of residues modular m. In other words, the difference between this and this is the following. Over here, these numbers do not have to be relatively prime with m. Over here, these numbers, the numbers from a reduced residue system, should be relatively prime to n. For example, consider 3. Note that a complete residue system modular 3 is 0, 1, and 2, because any integer is congruent to either 0 or 1 or 2 modular 3. Or if we use this lemma, we have indeed 3. So here we have 3. Indeed, 3 integers that satisfy the following condition. They are incongruent modular m. So any two integers here are incongruent modulo m. However, a reduced residue system modulo 3 is 1 and 2 only, because 0 is not relatively prime to 3. This is relatively prime, this is relatively prime, but 0 is not. Please take a look at Theorem 2. Theorem 2 says the following. If R1, R2, and so on are phi of n is a reduced residue system modulo n, and if a is a positive integer or relatively prime to n, then this set, we just multiply each number here by a, is also a reduced residue system modulo n. Here is how we prove it. So first, let us show that each such an integer is relatively prime to n. Let us show that a r j is relatively prime to n. Assume to the contrary that the greatest common divisor of this and this is greater than 1. Since the greatest common divisor of these two numbers is greater than 1, it has a prime divisor. Here we use the following theorem. Let me go back to this. Over here, this lemma says that every integer greater than 1 has a prime divisor. Since this integer is greater than 1, it has a prime divisor. So the greatest common divisor, let us denote it by d, divides this, p divides d, therefore by this theorem, p divides this. Now let us use theorem 2 from section 3.5. Let us look at this theorem. It's over here. This one. If p divides the product where p is a prime number, p divides one of these factors. So p divides this product. P is a prime number. Therefore, p divides either a, which is exactly what is written here, or p divides rj, which is exactly what is written here. Here is what we have. Since the greatest common divisor divides this, and p divides the greatest common divisor, again by transitivity, p divides n. So either p divides n and p divides a, which is over here, or p divides n and p divides rj, which is over here. Once again, p divides n in any case. But talking about this product, we have two possibilities. Either p divides a or p divides rj. So this is case 1, this is case 2. Now, we cannot have this because rj is a member of a reduced residue system modular n. Means Rj is relatively prime to n. So P cannot divide both n and Rj. Now note that this is also impossible. P cannot divide A and N simultaneously because according to what is written here, A and N are relatively prime. Since A and N are relatively prime, P cannot divide A and N. So this is impossible, this is impossible. We assume that the greatest common divisor is greater than 1. We got a contradiction. Therefore, the greatest common divisor is equal to 1. So we conclude that A, R, J, and N are relatively prime. Now let us finish our proof. Here's what is left. We have to demonstrate that there are no two ARJs that are congruent modular n. Again, let us assume to the contrary that ARJ is congruent to ARK, where J is not equal to K. Note that since A and N are relatively prime, by corollary 1 to theorem 7 from section 4.1, A can be cancelled. Let us go back to this theorem. Please take a look at this. If C and M are relatively prime, C can be cancelled. Done. That's exactly how we do it. A and N are relatively prime. It's written over here. Therefore, by corollary 1, we can cancel out A. Done. This is a contradiction because Rj and Rk came from the original set of a reduced residues modular n. And remember, by definition, no two different elements of the set are congruent modular n. So this is impossible by definition. Therefore, this is impossible. We are completely done. Now let us discuss the following example. This set is a reduced residue system modular 8 because here we have phi of 8 elements. These are pairwise relatively prime elements. Moreover, each of these elements is relatively prime to 8. Here is what we do next. Pick some integer which is relatively prime to 8. For example, 3. This integer does not have to be from this set. And then multiply each of these numbers by 3. 3 times 1 is 3. 3 times 3 is 9, 15, 21. By theorem 2 above, this set of the numbers 3, 9, 15, 21 is also a reduced residue system modular 8. And now let us prove theorem 3. Euler's theorem. If n and a are positive integers, moreover relatively prime integers, then a to phi of n is congruent to 1 modular n. Note that Fermat's little theorem is a particular case of theorem 3. Indeed, if n is a prime number, then phi of n is equal to n minus 1. Moreover, if n is a prime number and a and n are relatively prime, then indeed a is not divisible by n. This is exactly what we have in Fermat's little theorem. So Fermat's little theorem is a particular case of Euler's theorem. Let us prove Euler's theorem. Let R1, R2, and so on, R phi of n, denote the reduced residue system made up of the positive integers not exceeding n that are relatively prime to n. Here is what we do next. Let us multiply each of these numbers by a. Done. R1a is congruent to Q1 modulo n. R2a is congruent to Q2 modulo n, and so on, where these numbers are the least positive residues. We can use the division algorithm, divide each of these numbers by n, and find the remainder. Here is what we do next. If we multiply these numbers by a, the resulting set is again a reduced residue system modulo n by theorem 2 above, because a and n are relatively prime. In the appendix, we show that since this is a reduced residue system modulo n, then this is a reduced residue system modulo n. We will discuss this proof later. So, this is a reduced residue system. Therefore, this is a reduced residue system modulo n. However, remember, we don't say the reduced residue system. We say a reduced residue system. We consider some moduli, there are infinitely many reduced residue systems. However, please take a close look at both these and these reduced residue systems. Here we say R1, R2, and so on, R phi of n is a reduced residue system made up of the positive integers not exceeding n. Same is here. These are the least positive residues. Conclusion: these two sets are equal. Since these two sets are equal, if we multiply all these congruences together, we get this. But according to what is written here, since this set is equal to this set, this product is equal to this product. Now, a times a times and so on, a is a to phi of n. Since each of these numbers is a relatively prime to n, we can cancel out each number, and after the cancellation, we get exactly what we need. Folks, think about questions.
Could you explain what least positive residues means again?
Well, in simple words, these are remainders. We divide this by this, find the remainder. Done. We divide this by this, find the remainder. Done, and so on.
Could you go over the reasoning for why the two sets are equal?
Yes, so it's a very good question. By the way, note that the proof is not complete yet because we have to prove that these numbers form a reduced residue system modulo n. But now, note that in both sets, we have the same number of elements, phi of n. Remember, phi of n numbers are all positive integers, not exceeding n that are relatively prime to n. In both sets, these numbers do not exceed n. In both sets, we have numbers that are relatively prime to n. In both sets, we have numbers that are pairwise relatively prime. So there is no escape. This set is equal to this set.
Perfect. I see it now. I forgot that we've proved that the Q's are a reduced residue system.
We have not proved it yet.
Oh, I see.
We prove it in appendix. We are about to prove it. Any other questions before we discuss the proof?
So the key takeaway here is that the reduced residue system that exists less than n and consists of only positive integers is unique.
Yes.
Okay.
It's unique. Now let us prove this. Please take a look at the appendix. Here we show that Q1, Q2, and so on, Q phi of n is a reduced residue system modulo n. So we first show that each integer Qj is relatively prime to n. Assume to the contrary that the greatest common divisor of Qj and n is greater than 1. Since this integer is greater than 1, by this lemma, it has a prime divisor. So the greatest common divisor divides this and this. P divides the greatest common divisor. Therefore, P divides this and this. But now remember, what are these numbers? Qj is congruent to Rja. This is how we created these Qs. So, since this is congruent to this modulo n, this minus this is divisible by n. So this minus this is equal to nk. Therefore, Rja is nk plus Qj. But now, as we discussed, P divides this and this. Since P divides both Qj and n, P divides the whole right-hand side. Conclusion, P divides the left-hand side. It's exactly what is written here. P divides Rja. But now, since P is prime, if P divides the product, it divides either factor number 1 or factor number 2. We use this theorem. So there are two possibilities. Either P divides A, this A, or P divides Rj, this Rj. Also note that P divides n. It's exactly what we have here. So we have two possibilities, either this or this. However, this is impossible because Rj is a member of a reduced residue system modulo n. And this is impossible because A and N are relatively prime. Conclusion: Qj and N are indeed relatively prime. Lastly, in order to prove that there are no two Qj's that are congruent modulo N, we assume to the contrary that they are. Now, if this is true, remember Qj is Rj minus Nk. If this is true, these guys are congruent. It's exactly what we have over here. But remember, N and A are relatively prime. Therefore, A can be cancelled out, and we have Rj is congruent to Rk. Cannot be. These R's form a reduced residue system modulo N. They have to be incongruent. So we assume this, we got a contradiction, therefore this is not the case. So this proof is very similar to this one. Lastly, let us discuss few examples. So remark one, know that Fermat's little theorem follows immediately from Euler's theorem, because if n is a prime number, phi of n is n minus 1. Please take a look at remark 2. We can use Euler's theorem to find inverses modulo n. Let me remind you what is inverse modulo n. Let us go back to section 4.2. Suppose A and M are relatively prime, then an inverse of A modulo M is a solution, an integer solution of these congruents. So X is an inverse of A modulo M. Here's what we do next. Note that by Euler's theorem, A to phi of n is congruent to 1 modulo n. Note that A to phi of n can be rewritten as A times A to phi of n minus 1. Conclusion: if you replace this by x, you will get X is congruent to 1 modulo n. It's exactly what is written here. Therefore, this is indeed an inverse of A modulo n. So, in order to find inverse of 2 modulo 9, we raise 2 to the power phi of 9 minus 1. Phi of 9 is 6, 6 minus 1 is 5, 2 to 5th power is 32, 32 is congruent to 5 modulo 9. Conclusion: 5 is an inverse of 2 modulo 9. Actually, any of these numbers is an inverse of 2 modulo 9, but the easiest answer is 5. Now, let us go back to section 4.2 again. In this section, we discussed the following corollary that says the following. In order to find a solution of these congruents, first, we find a solution of these congruents. S, we find an inverse of A modulo M, and then multiply B by S. Now, suppose we have these congruents, we know how to find inverse of A modulo N. Here is the inverse. Therefore, by this corollary, in order to find a solution of this congruence, we just multiply this by this. It's exactly what is written here. A to phi of n minus 1 times b modulo n. For example, one way to solve this is to multiply 7, which is over here, by 3 to this power. Remember, a is equal to 3. And then after all computations, we get the following result. X is congruent to 9 modulo